Hello students, today we'll cover part 2 of your chapter 10 Haloalkanes and Haloarine, class 12 science chemistry. Let's start. Here we'll see the nature of CX bond, that means carbon halogen bond that is present in the haloalkanes. Now we know that halogen they belong to group 17 and carbon belong to group 14. And when we move from left hand side to right hand side, that means from 14 when we'll go towards the group 17, electronegativity increases. So out of carbon and halogen, halogen is more electronegative. Electronegativity is the nature by which the element attract the shared pair of electron toward itself. So what happen in haloalkanes when we get the CX bond, this halogen being more electronegative, it will attract the shared pair of electron toward itself. Now when electron accumulate more towards the halogen, it will give negative charge on the halogen atom. Partial negative charge will develop on the halogen atom. And here carbon is being deprived from its shared electron and hence it will accumulate some positive charge on it. So basically what happened here, earlier it was a covalent bond, equal sharing was there, but due to the electronegativity difference between carbon and halogen, the bond become polar. Partial charge develop along the two poles of the bond. Now, due to this polarity, the properties of the haloalkanes impact, or the properties are different due to this polarity than compared to your other hydrocarbons. Now, halogen means fluorine, chlorine, bromine and iodine in a group, and when we move from top to bottom in a group, then what happens? The size of the halogen increases. Now, if this atom is getting bigger and bigger, the carbon halogen bond length also increase, and for a longer bond length, the bond energy decreases, the bond become weak. So if you compare the bond between carbon and fluorine, it will be much stronger than the bond between carbon and iodine, because iodine is bigger in size as compared to your fluorine. Now we'll see the preparation of haloalkanes and haloarines here. The first preparation is from alcohol. We'll try to derive haloalkane from alcohol. The process can be done by using a variety of reagent such as PX2, that means phosphorus halide. Then we can also take the mixture of HX and ZnCl2, anhydrous ZnCl2. Do remember this reagent is called Lucas reagent. It is being used to detect the alcohol, whether it is 1 degree, 2 degree or 3 degree alcohol. Next reagent you can use is red phosphorus along with halogen, but here the halogen you must choose as bromine and iodine. If you want chloroalkane, then the option is PCl5 and PCl5 or thionyl chloride, SOCl2. Now in case of thionyl chloride, there is a advantage that whatever byproduct you will get in this reaction, if you are trying to convert alcohol into haloalkane by using this thionyl chloride, the byproducts are SO2 and HCl. Both are in gaseous state. So you will just get the haloalkane product and other gaseous byproduct will goes off. So that is an advantage of using thionyl chloride. Next preparation is from alkene. Now from alkene you can get haloalkane by the process of Markovnikov addition and anti-Markovnikov addition. In class 11 we studied detail about it, hope you remember that. So if you apply this Markovnikov and anti-Markovnikov addition reaction on alkene by reacting alkene with some HBr or HX, then you might get haloalkane. Third process is from hydrocarbon, that means from alkane you may get haloalkane on treatment with halogen in presence of sunlight, UV light. This is a free radical mechanism, and in this reaction you get a series of haloalkane. Here you get a polyhaloalkanes. That means if you have started from CH4, Suppose you have you are doing the reaction with CH4 plus Cl2 in presence of sunlight in this free radical mechanism. You will get a series of product. You might get CH3Cl, you might get CH2Cl2, you might get CHCl3, you might get CCl4. That means polyhalogenated compounds are also possible in this reaction, and it happens on a chain reaction mechanism. Next is very important is your halogen exchange method. Now in halogen exchange method, you start from an haloalkane, and there the halo part you will substitute with your desired halogen. Suppose you are starting with RBr, okay, or RCl. You have chosen chloroalkane or bromoalkane, and you want iodoalkane. So in that case, what you will do, you will treat it with sodium iodide. Then iodine, being a halogen, will replace the halogen already present in haloalkane, and you will get iodoalkane. This reaction is called Finkelstein reaction. Then if you want fluoroalkane, in that case you will start from bromoalkane, you will treat it with silver fluoride, you will get fluoroalkane, and the byproduct. The name of the reaction is SWOT reaction. Whenever you get a name for the reaction, these are called name reaction, and these are very important. Now sometimes the student get confused with the Finkelstein and SWOT reaction because both are halogen exchange reactions. So there is a trick to remember it. You just see the term Finkelstein here. I you are getting 2 times. So whenever it is Finkelstein, do remember it should give iodoalkane as a product, and you choose the reagent in accordance. Next is the preparation of haloarine. Now haloarine preparation we can do with the electrophilic substitution reaction. So we'll start with a toluene. You'll treat it with halogen X2, any halogen, along with a promoter or a catalyst iron in dark, okay, in absence of sunlight. Then we get 2 derivatives, one ortho and one para product. At ortho position, one halogen will get attached, and in para position it will get attached. Out of these 2, which one is stable? This para isomer will be more stable over this ortho. So in the reaction, para isomer will be more in percentage, it will form more than your ortho derivative. The same reaction you can carry out. You will take toluene, you will take halogen, but you will be doing the reaction in presence of sunlight. In that case, you will get benzyl alkane. That means here you are getting haloarine, but in this case you are getting haloalkane. Next is your Sandmeyer reaction. This is very important reaction. Now in this Sandmeyer reaction we start from aniline. So this is your aniline compound, benzene with NH2 group. So here your target is to remove this NH2 group and to place one halogen here. But this NH2 group is very much stubborn. Directly you cannot remove it. So what is being done? It is being converted into a intermediate state or intermediate product. Therefrom the further reaction is being carried out. So aniline, if you want to convert it into anything, or you want to remove this NH2 group, always the first step you have to do. So this is being done with a process by using NaNO2 plus hydrogen halide. See the temperature 273 to 278. It means what? The temperature is around 0 to 5 degrees centigrade. That means you have to carry out the reaction under very low temperature, and you will get benzene diazonium halide. This is also called diazonium salt because you are getting plus minus charges. Now this derivative is very much unstable. If you increase the temperature, then also this will degrade. So once you get this diazonium salt, you will treat it with Cu2x2, and this N2 plus X minus part will be replaced with halogen. From the same diazonium salt, if you treat it with copper and hydrogen halide, then also the same reaction happen. You can also try it with some Ki. So you'll get here iodine. So once you get this product, this intermediate product, here from you can follow different route to get your desired haloarenes. Now, the first step of Sandmeyer reaction is also known as diazotization reaction. So, sometime one more question come, what is diazotization reaction? In your answer, you must write this first reaction. You will start from aniline, you will treat it with NaNO2 plus HX under very low temperature. The temperature is also important here. It's not heat, you are not heating here unless like other cases, but here you have to maintain low temperature. You get a benzene diazonium halide salt, and this reaction is called diazotization reaction. Now, what is the meaning of the term azo? Azo means di. It's not due to this di. Here di means two nitrogen is there, that's why it is di. But azo means dye, dye, that means color. So whatever color you are getting, it is just because of this intermediate product. In the lab also you have to perform this reaction to make the organic dye compounds. Next we'll see the properties of haloalkane. So here we'll discuss about the physical state, boiling point, and solubility and density of the haloalkane. Now what about the physical state? Haloalkanes with the lower molecular weight, they exist as gas. As you increase the molecular weight, slowly they will go to the liquid state and then to the solid state. So haloalkane with the higher molecular mass is available in the solid state. If it is with a lower molar mass, then we can expect that that will be in the gaseous state. Iodine is a bigger molecule with a great atomic mass, so haloiodides are generally solid, but lower chloroalkanes like CH3Cl, then CH3Br, this exists as a gas. These are colorless compound. Generally haloalkanes are colorless compound, but if you are chosen bromoalkane and iodalkane and somehow exposed to light, then sometimes they impart the color as well. They are volatile compound, they have a sweet smell. Okay, so these are some of the physical properties of the haloalkane. Next we see the boiling point. Now look at this graphical presentation. Here this red part is for chlorine, blue is for bromine, and I is for iodine. They had given an approximate values, statistical representation they had given. So if you have chosen CH3X, then your haloalkanes, okay, haloalkanes are having the lowest boiling point, then bromoalkane, then iodalkane. When you are increasing the molar mass, here you have chosen C2H5X for chlorine, that means if you are choosing C2H5Cl, then it is having a value which is higher than that of CH3Cl, okay, but this value is again lower than that of bromoalkane and iodoalkane. So here from what we can conclude that as the molar mass increases, the boiling point of haloalkane also increases. That means boiling point is directly proportional to the molar mass of the compound. Iodine is bigger in size, it is having more mass, so iodoalkanes are always having the higher value. So hope you understood this part. So what is the trend? The trend for boiling point goes as RF, that means fluoroalkane is having lower boiling point than that of chloroalkane, then bromoalkane, then iodoalkane. Iodoalkane is having the greatest boiling point. Next, boiling point of chloride, bromide and iodides are considerably higher than those of the hydrocarbon of comparable molar mass. So if you have chosen one hydrocarbon and you are comparing with the haloalkane, where H is being replaced with halogen. Now see, what is the atomic mass of hydrogen? It is 1. And what will be the atomic mass of chlorine? 35 onwards. So obviously it will be having more mass. This Rx will have more molar mass, and we already know boiling point is directly proportional to molar mass. So if you compare between hydrocarbon and parent hydrocarbon and that of its halogen derivative, then the halogen derivative haloalkane will have more molar mass than the parent hydrocarbon. So if you are given CH4 and CH3Cl, then CH3Cl will have more boiling point than that of CH4. Next, boiling point trend given here, some values are given. You see, it is the isomers of bromoalkane. Okay, so it is normal bromoalkane, normal bromobutane. Here it is iso and here it is neo. The values are decreasing. Here it is 375 boiling point, here it is 364, 346. Here you see it is straight chain. Okay, here you are getting branch and here the branching increases. So when you increase the branching, the boiling point decreases. Now why it decreases? The reason is, with the branching the surface area reduced, the van der Waals force of attraction will be lesser. So boiling point also depend on the van der Waals force of attraction, that is again proportional to the surface area. So more is the surface area, more is the boiling point. So with branching for the same isomer, boiling point decreases. Now come for the arene part. Now here what happened, we have chosen ortho derivative, then meta derivative and para derivative. It is like ortho dichlorobenzene, meta dichlorobenzene and para dichlorobenzene. Here the highest value is for the para isomer, 448, 453, 446, 448. For para isomer this is the highest. Why it is the highest? Because this molecule is symmetrical. So when we get it in a packing, they are having a good packing. We cannot remove it easily. The packing efficiency is very high, so it is being very difficult to separate the molecule from each other, and hence they are having the highest boiling point. Okay, so that is all about your boiling point. Next is your solubility. So there is a myth or general rule, we know that like dissolve like. So if you have the polar solute, it will be soluble in polar solvent, and if you are having a non-polar solute, it will be easily soluble in non-polar solvent. Now what about the solubility of haloalkane? Just now in the beginning of this topic we have studied that haloalkanes are polar in nature due to this polar CX bond present in them. Now this is slightly polar, so we can expect that haloalkanes are slightly soluble in polar solvent. Polar solvent is what? Polar solvent is water. But if the molar mass increase, the solubility will decrease. Now why the solubility will decrease with the increasing molar mass? Because if your R group become bulkier, okay, being hydrocarbon, it repel water. This hydrocarbon part is not easily soluble in water. That is one reason. Second reason is that to make anything soluble in water, there must be two kind of bond arrangement is involved. One is, with water the solute will form a bond, that means formation of bond will happen, and the breaking of the alkane halogen is also involved. Now the energy that is being evolved from the formation of new bond is not sufficient enough to break the previous bond present. So solubility of the haloalkane decreases in water. Moreover, they are not able to form hydrogen bond from this R part. So solubility in water is less. With increase in molar mass, it decreases. Next is your density. Now bromo, iodo and polychloro derivative of hydrocarbons are heavier than water. Okay, do remind it, polychloro, they have not said chloro. Bromo and iodo is fine, it's mono, but polychloro derivatives of hydrocarbons are heavier than water. Now what is the density of water? The density of water is around 1. Now see the values given here. You got a bromo derivative, bromopropane, then iodopropane. The values are given more than 1, 1.3, 1.7, so on. Polyhalo, okay, polyhalo derivatives are also having the values. Now here to here you see the values is increasing. How it is increasing? More is the chlorine, more is the number of chlorine, heavier is the molecule, and greater is the value. Okay, in case of monochloro derivative, what happened? The value is less than 1. So bromo, iodo and polychloro derivative of hydrocarbons are heavier than water. But if it is monochloro, then the value will be lesser than 1. That means their density is less. One numeral, let's solve it. So you are given, arrange each set of compound in order of increasing boiling point. You are given bromomethane, bromoform, chloromethane, dibromomethane. So we know that how boiling point change, or how it depend on the molecule given. It depend on the molar mass of the molecule. So bromomethane formula is CH4, sorry, it must be CH3Br. Please correct this one. It must be CH3Br. Bromoform is CBr4. Chloromethane is CH3Cl, and dibromomethane is your CH2Br2. Now you see the maximum, here you are getting maximum number of bromine, molar mass will be obviously higher. So this will have the highest boiling point. Then here you are getting 2 bromine, this must be the second, this must be third. Please do correct it, CH3Br it should be, it must be third, and last you are having a chlorine with a lower molar mass, so it must be the fourth. So your arrangement will be in increasing order they had given. So your arrangement will be, you'll start from the fourth one, CH3Cl is lower than your CH3Br, then CH2Br2, and at last CBr4 with the highest value. So that's all for today. Thank you.